All right, let's unpack this. You sent us a fascinating chapter on the structure of crystalline solids. Lots of diagrams and equations. Don't worry, we're here to help you break it down.
It's like a blueprint for how atoms arrange themselves in solid material, and believe it or not, this can dramatically affect things like strength, transparency, even how a material reacts in a chemical process.
So we're not just talking about what something looks like. We're talking about how strong it is, whether it's transparent, even how it behaves in chemical reactions.
Exactly. Imagine trying to build a house without understanding the properties of wood, brick, and concrete. It's the same with material science. We need to understand the building blocks to create anything useful.
Okay, I'm starting to see the foundation here. So where do we begin?
First, we need to differentiate between crystalline and non-crystalline structures. Imagine perfectly stacked oranges at a grocery store. That's your crystalline solid, with atoms arranged in a precise repeating pattern. Now, picture a bowl of jelly. That's more like a non-crystalline or amorphous structure, with atoms in a more random arrangement.
Okay, I'm getting the visual. Order versus disorder. Is that why some materials are transparent while others are opaque?
You got it. The way those atoms are arranged plays a key role in how light interacts with the material, and that affects its transparency. Think about glass versus ceramic.
Fascinating. So how do we break down these crystalline structures? Is there some kind of basic unit that repeats?
Absolutely. We call them unit cells. Think of them like Legos. Each brick is a unit cell, the smallest repeating unit in a crystal. Just like you can build endless structures with the same Lego brick, different crystals are formed by arranging these unit cells.
Okay, so the unit cell is our blueprint. Are there different types of these building blocks?
And there are actually quite a few, but we'll focus on three common ones found in metals: face-centered cubic, FCC, body-centered cubic, BCC, and hexagonal close-packed, HCP.
All right, let's break those down. What's the FCC structure like?
Picture a cube with an atom at each corner and one in the center of each face, hence the name face-centered. A lot of metals we use every day, like copper, aluminum, silver, and gold, have this structure.
Okay, so FCC is a cube with atoms at the corners and faces. Got it. What about BCC?
BCC is also a cube with atoms at each corner, but this time there's an atom right smack in the center of the cube itself. Metals like chromium, iron at room temperature, and tungsten have this structure.
Right, another cube, but with a different atom placement. Makes sense. Now, HCP is the trickier one, right?
Yes, HCP is a bit more complex. Imagine a stack of hexagonal layers, kind of like a honeycomb, with atoms at each corner and one in the center. Metals like magnesium, titanium, and zinc crystallize in this way.
I'm seeing the honeycomb in my mind's eye. You know, it strikes me that these different unit cells are sort of like packing spheres together in different configurations. Is there a connection there?
You're absolutely right. The way those atoms are packed together is crucial for understanding a material's properties. We talk about coordination number, which is just how many neighbors each atom has in the structure.
So it's like the atom's social circle. The more neighbors, the more connected it is.
Exactly. And then there's the atomic packing factor, or APF, which measures how efficiently the atoms are packed together in the space. Think of it as how tightly you can pack oranges in a box.
So a higher APF means a denser material. I'm guessing this is where we get into calculating density from the textbook.
You've got it. Knowing the crystal structure allows us to calculate a material's density and even predict the density of new materials.
That's incredible. We're really starting to see how the arrangement of atoms affects the material's properties. But wait, I remember reading about materials that can change their crystal structures, like some kind of atomic transformers. What was that called? Polymorphism.
That's right. Polymorphism means a single material can have different crystal structures, depending on factors like temperature and pressure. It's like having a wardrobe change at the atomic level.
Okay, so a material can morph depending on the conditions. Got any mind-blowing examples of this?
Carbon is a classic example. Graphite, the stuff in your pencil, and diamond, the hardest natural material we know, are both made of carbon atoms. The only difference is their crystal structure.
Wow, so the same element can be soft and dark, or incredibly hard and sparkly, all thanks to different atom arrangements. That's wild. Any other examples of this polymorphism?
There's a rather dramatic one involving tin. Remember the story of Napoleon's army and their tin buttons?
Wait, is this the one where their buttons crumbled in the extreme cold? What does that have to do with the crystal structures?
It's all about polymorphism. Tin can actually disintegrate in extreme cold because it undergoes a transformation from white tin to gray tin, which has a completely different crystal structure and is much weaker. Imagine the chaos when those buttons started falling apart.
No wonder they called it tin disease. So this polymorphism isn't just a scientific curiosity. It can have real-world consequences.
Absolutely. Understanding these transformations is crucial for designing materials that can withstand specific conditions.
Okay, I'm thoroughly convinced that these crystal structures are more than just pretty patterns. But how do scientists actually keep track of all these different structures? It seems like there could be an infinite number of possibilities.
There are countless possibilities, but thankfully there's a system for categorizing them based on the geometry of their unit cells. We call these the 7 crystal systems.
Mhm.
Think of them as the basic families of crystal structures.
So instead of memorizing every single crystal structure, scientists can group them into these 7 families. I like where this is going.
Exactly. This system helps us predict and understand the properties of different crystals based on which family they belong to. It's like knowing that a lion and a tiger, while different, share certain characteristics because they're both felines.
Clever. And I'm guessing this is where we get into the nitty-gritty of measuring those unit cells. What do we call those measurements again?
We call them lattice parameters. These are the measurements that define the shape and size of the unit cell. It's like measuring the length, width, and height of our Lego brick as well as the angles between its faces.
Okay, so lattice parameters give us the dimensions of our building block. But what about navigating within those 3D structures? How do we describe specific locations, directions, or even planes within a crystal? It seems like we'd need a special language for that.
You're right, and we do have a special system for that. It's called Miller indices. It's essentially a coordinate system for crystals, like a GPS for navigating the atomic world.
Miller indices. Sounds a bit intimidating, but I'm intrigued. Give me the basics.
Imagine slicing through a crystal at different angles. The Miller indices tell us exactly where those slices are and how they relate to the underlying crystal structure. It's a way to precisely describe specific planes and directions within the crystal lattice.
Okay, I'm starting to see how this all fits together. We've got the basic building blocks, unit cells, a way to categorize them, crystal systems, and a system for describing locations and planes, Miller indices. What else is crucial for understanding these crystalline structures?
There are a few more key concepts that help us understand how materials behave at the atomic level. One of them is linear density. Imagine a line of atoms along a specific direction in the crystal, kind of like a string of pearls.
Okay, got the pearl necklace visual. How does linear density relate to that string of atoms?
Linear density tells us how closely packed those atoms are along that specific direction. It's basically the number of atoms per unit length, so a higher linear density means a tighter arrangement.
So a higher linear density means those atoms are huddled closer together. I bet that influences how the material behaves, right?
Absolutely. And we have a similar concept for planes of atoms called planar density. It describes how densely atoms are packed on a specific crystal plane. These densities play a big role in determining how materials deform under stress, like when you bend a metal or stretch a rubber band.
Okay, so linear density is about lines of atoms, planar density is about planes of atoms, and both can influence a material's strength and flexibility. Got it. Now, what about those super efficient FCC and HCP structures we talked about earlier? They seem like the rock stars of crystal packing.
They are. We call them close-packed structures because they achieve the highest possible density for a given atom size. Imagine stacking layers of spheres as tightly as you can. That's essentially how atoms arrange themselves in these structures.
So they're like the champions of spatial efficiency. I'm guessing these close-packed structures have some pretty impressive properties.
You bet. They often exhibit excellent strength and ductility, which means they can be deformed without breaking. That's why metals like aluminum, FCC, and titanium, HCP, are so popular for structural applications where strength and flexibility are key.
This is all making so much sense. But wait a minute. I remember reading that most materials aren't actually single crystals, but rather polycrystalline, made up of many tiny crystals or grains. How does that change things?
That's a great question. It's true that a perfect, uninterrupted crystal structure extending over a large distance, what we call a single crystal, is actually quite rare. Think of gemstones, like the garnet in your textbook.
Yeah, those single crystals are definitely impressive, but most materials we encounter in everyday life are not like that. So how do all those tiny crystals fit together in a polycrystalline material?
Imagine a mosaic made of many tiny tiles. That's a good analogy for a polycrystalline material. Each tile is a tiny crystal or grain, and they all have slightly different orientations, kind of like a jumbled up version of a single crystal.
So it's like a patchwork of crystals all stitched together.
Exactly. And where those grains meet, we have a boundary region called a grain boundary. You can think of it like a seam in our mosaic.
Interesting. So do these grain boundaries make the material weaker because of those mismatches?
It's not that simple. Grain boundaries can actually make a material stronger. They act as obstacles to the movement of atoms within the material, making it harder for the material to deform. But they can also make the material less ductile, meaning less able to bend without breaking.
So it's a trade-off. More strength, but potentially less flexibility.
Fascinating. This is all incredible stuff, but I have to ask, how do scientists actually see these crystal structures? They're so tiny.
That's where one of our most powerful tools comes in, X-ray diffraction.
X-rays. So we're talking about something like taking an X-ray of your bones, but at an atomic level.
Precisely. By analyzing how X-rays diffract or scatter off material, we can actually determine the arrangement of atoms within it. It's like having X-ray vision for the atomic world.
That's incredible. So by shooting X-rays at a material, we can map its internal structure all the way down to the arrangement of atoms.
Exactly. And from there, we can begin to understand and even predict the properties of that material, which is the foundation for designing new materials with incredible properties. This is mind-blowing. Okay, we've covered a lot of ground here, from unit cells and crystal systems to X-ray diffraction. It's like we've learned a whole new language to describe the hidden world of materials.
And we're just getting started. In the next part, we'll dive deeper into X-ray diffraction and explore how we can use this powerful tool to decipher the secrets of crystal structures.
All right, I'm ready to put on my X-ray vision goggles. We left off talking about how X-ray diffraction helps us see those tiny crystal structures. But how exactly does that work?
It's all about how those X-rays interact with the atoms in the material. When X-rays hit a crystal, they get scattered in different directions by the atoms.
Okay, so the X-rays bounce off the atoms?
Sort of, it's more like they get deflected or diffracted by the electrons in the atoms. And the way they scatter depends on the arrangement of those atoms in the crystal structure.
So the scattered X-rays carry information about the crystal structure.
Exactly. It's like shining a flashlight into a maze. The way the light reflects off the walls tells you about the shape of the maze. Similarly, the pattern of scattered X-rays tells us about the arrangement of atoms in a crystal.
That's a great analogy. But how do we actually make sense of those scattered X-rays? It's not like we can just see them with our eyes.
We use a detector that can measure the intensity of the scattered X-rays at different angles. This gives us a diffraction pattern, which is basically a graph showing the intensity of the X-rays as a function of the scattering angle.
So we're looking for patterns in the way those X-rays bounce off the crystal.
Precisely. And those patterns are directly related to the spacing between the planes of atoms in the crystal lattice. That's where Bragg's law comes in.
Ah, Bragg's law. I remember seeing that equation in the textbook. What exactly does it tell us?
Bragg's law basically tells us the conditions required for those scattered X-rays to reinforce each other, creating a strong signal. It relates the wavelength of the X-rays, the spacing between the atomic planes, and the angle at which the X-rays hit the material.
So it's like a formula for finding those sweet spots where the X-rays line up perfectly and give us the strongest signal.
Exactly. By analyzing the angles and intensities of those strong signals, we can calculate the distances between those atomic planes.
It's like using X-rays in math to measure the distance between atoms. Pretty clever.
Yeah.
But I'm curious, do all crystals produce the same kind of diffraction pattern?
Not at all. The arrangement of atoms within the unit cell can actually cause some of those scattered X-rays to cancel each other out. So certain diffraction peaks might be missing or weaker depending on the specific crystal structure.
So it's not just about the spacing between the planes, but also the arrangement of atoms on those planes.
You got it. It's like having a hidden code embedded in the diffraction pattern that tells us the exact arrangement of atoms within the crystal.
And scientists have figured out how to crack that code for a lot of different materials, right?
Absolutely. We have extensive databases of diffraction patterns for thousands of materials, so we can often identify a material just by looking at its diffraction pattern. It's like a fingerprint for crystals.
Okay, so we've explored how X-ray diffraction helps us understand the arrangement of atoms in crystalline materials. But what about those materials that aren't crystalline? The amorphous or non-crystalline ones, do they diffract X-rays at all?
They do, but their diffraction patterns look very different from those of crystalline materials.
Why is that? Don't they still have atoms?
They do, but remember, amorphous materials lack that long-range repeating order that we see in crystals. Their atoms are arranged more randomly, like the molecules in a liquid.
Right, back to that bowl of jelly. So what does their diffraction pattern look like?
Instead of those sharp, distinct peaks that we see for crystals, Amorphous materials produce a more diffuse, spread-out pattern. It's like the difference between a clear, focused image and a blurry one.
So we can still learn something about the structure of amorphous materials from their X-ray diffraction patterns,
Yeah.
even if it's not as precise as with crystals.
Exactly. The shape and width of that diffuse pattern can give us information about the average distances between atoms and the degree of order in the material.
Fascinating. It seems like X-ray diffraction is a really versatile tool for exploring the structure of materials, whether they're perfectly ordered crystals or more random amorphous structures. It's like having a superpower that lets us see the invisible.
It really is. And it's not just about seeing the structure.
Yeah.
By understanding the structure, we can start to understand the properties of materials and how we can manipulate them to create new materials with specific properties.
That's what's so exciting about this, right? It's not just about understanding what's already there, it's about creating something new. But we're not done with the textbook yet. There's still more to explore, right?
We've only just scratched the surface. In the next part, we'll move beyond single crystals and delve into the fascinating world of polycrystalline materials, where those tiny grains and their boundaries create a whole new layer of complexity.
All right, let's talk about these polycrystalline materials. We left off with the idea that they're like mosaics of tiny crystals, each with its own orientation. What kind of impact does that have on a material's properties?
It's a huge factor. Think about it. Those grain boundaries where those tiny crystals meet, they're essentially disruptions in the otherwise perfect order of the crystal lattice.
So are those boundaries a good thing or a bad thing?
Well, it depends on what you're looking for in a material. Those grain boundaries can actually make a material stronger, believe it or not.
Wait, so imperfections can actually make something stronger? How does that work?
It seems counterintuitive, but it's true. Those boundaries act as obstacles to the movement of atoms within the material, making it harder for the material to deform permanently.
So it's like trying to move a crowd through a narrow doorway. It slows things down.
Exactly. And by controlling the size and distribution of those grains, we can actually fine-tune a material's strength. Smaller grains, more boundaries generally means a stronger material.
So it's not just about the crystal structure itself, but also about how those crystals are arranged within the material.
Precisely. It's like building a brick wall. The individual bricks are important, but the way you arrange them and the mortar you use to hold them together also play a crucial role in the overall strength of the wall.
That makes sense. It's all about understanding the structure at multiple levels. So are there other ways to manipulate a material's properties by playing with its structure?
Oh, absolutely. We can introduce different atoms into the crystal lattice, creating what we call alloys.
Like mixing different types of Legos to create a stronger or more colorful structure.
That's a good way to think about it. By adding those foreign atoms, we can disrupt the neat arrangement of the original crystal and create a whole new set of properties.
So we're not just stuck with the materials as they occur in nature. We can actually tweak their properties by tinkering with their structure at the atomic level.
Exactly. That's one of the most exciting things about material science, the ability to engineer materials with specific properties to meet our needs.
That's incredibly powerful. Okay, we've covered a lot of ground here, but there's one term from the textbook that I still don't quite grasp. Anisotropy. What does it mean for a material to be anisotropic?
Anisotropy means that a material's properties can vary depending on the direction in which they're measured.
Can you give me a real-world example of that?
Think about wood again. It's much easier to split wood along the grain than against it. That's because the wood fibers are aligned in a specific direction, giving the wood different strengths in different directions.
Right, that makes sense. So wood is anisotropic because its properties depend on the direction.
Yeah.
But what causes those directional differences at the atomic level?
It all comes down to the arrangement of atoms and the bonds between them. In an anisotropic material, the spacing between atoms or the types of bonds might be different in different directions.
So it's like having a material with different personalities depending on which way you look at it.
That's a great way to put it. And while single crystals are often anisotropic, polycrystalline materials, those mosaics we've been talking about, can actually appear isotropic, meaning the properties are the same in all directions.
But wait, how is that possible if each individual grain is anisotropic?
It's all about the arrangement of those grains. If they're randomly oriented, then their individual anisotropies tend to average out, resulting in a material that behaves the same in all directions.
So it's like taking a bunch of magnets with different poles and jumbling them up in a bag. The overall magnetic field of the bag would be pretty weak because the individual magnets are pulling in different directions, canceling each other out.
That's a fantastic analogy. And understanding anisotropy is incredibly important for engineers who are designing materials for specific
I
applications.
can imagine. You wouldn't want to build an airplane wing out of a material that's much weaker in one direction than another.
Exactly. You need to consider the directional properties of materials to ensure they perform as expected under stress.
This deep dive has been incredible. We've gone from the basic building blocks of crystals to understanding how their arrangement can impact a material's properties in such complex ways.
It really highlights the beauty of material science, how something as seemingly simple as the arrangement of atoms can create such a diversity of materials and properties.
And it's not just about understanding what's already out there. It's about designing and creating new materials with specific properties to solve problems and shape the future.
Exactly. Who knows what incredible materials we might create in the future as our understanding of crystal structures and their manipulation continues to grow.
Well, dear listener, the next time you pick up your phone, look out your window, or admire a piece of jewelry, take a moment to appreciate the incredible world of atoms that lies beneath the surface. It's the arrangement of those tiny particles that gives those materials their unique properties, making our modern world possible. We hope this deep dive has opened your eyes to the fascinating world of crystal structures and sparked a curiosity to explore even further. This was a deep dive. What stood out to you? We'd love to hear your thoughts. Let us know.